There are so many dark clouds in modern physics. Let's go back to classic physics of early 1900s and ask classic questions for elemental particles. Maybe it is time to revisit quantum mechanics and theory of general relativity. This is our new direction of physics.
Today we're going to do a presentation of the new direction of physics. In the next 15 video, we're going to present a self-interacting field theory. It will be different from the current mainstream physics. It's a new direction of physics. Back in the history of 1900, early 1900s, there are saying that there are two dark clouds in physics. Okay. So the Michelson-Morley experiment found that there is no ether. That means wave or photon is different from normal waves. There is no media to propagate the photons or radiation. Okay? So that's led to Einstein to repropose all Newton's equation of motions or Newton's law into a new frame. Under the Lorentz transformation, the physics law doesn't change. Okay, so there's another one. It's called ultraviolet catastrophe in black body radiation, because the black body radiation has a certain pattern. If you want to calculate the total energy of the radiation, so you integrate all wavelengths, then you get infinities. Okay, so that's what they call ultraviolet catastrophe in the early 1900s. So what Planck did is introduce a concept: the radiation is quantized. So once it's quantized, it has a Planck term. So that's solved the infinity problems in the early 1900s. Okay, so 120 years later, now today, there are more dark clouds in the sky of modern physics. Yeah, the modern physics is different from classic physics. This is the starting point of modern physics. Okay, there are now, for example, there are infinities in the quantum field theory. Okay, there are infinite number of infinities of quantum gravity. Okay, so that's infinity problem. We have only one infinity over here. Now we have infinity of infinities. It's almost like impossible to solve it. Okay, so the quantum gravity, it's not only this problem, also there is another problem, that the general relativity and the quantum mechanics, they're incompatible, because these two theories fundamentally different. Okay, about the prediction. Quantum mechanics saying that from A to B, it's statistically, but gravitation is saying, general relativity is saying, okay, from A to B, it's predetermined. We'll get back into this. Okay, so the vacuum energy and dark matter issues are the most, I think it's very serious issues. I think the current main problems is the incompatibility between the quantum physics and the general relativity, the number of infinities for quantum gravity. But I think the most important one is dark matter issues. So the dark matter issue, that's the most important one. Because currently, mainstream physics, they start investing resources into finding dark matter. They hope to find the dark matter, then solve all the physics problems. That's one direction, it's to find the dark matter. Okay, dark matter. Okay, so the theory I'm going to propose, it's not try to find the dark matter, but using a different theory. Okay, so instead of that, okay, I'm using a new theory. Okay, Okay, so in order to point out a new direction of physics, we need to get to the fundamental physics point of view. Okay, philosophically, what's wrong with the current direction? But as a physicist, we need to go back to the classic physics to ask classic questions instead of using mathematics. Okay, we have a lot of mathematics now. Okay, I'm going to ask some very classic questions. So the first question I asked in 1989, I was in graduate school. So I was asking many physicists, okay, and if there's a black hole, okay, what comes out of the black hole to attract the material? We have a black hole here over here. Now if we have a material over here, a test particle over here, so what comes out? The current mainstream physics is saying, I don't care, okay? Field theory, Einstein has a field theory equation. We follow that equation. We find how the test particle moves. But what comes out? So the mainstream have a conflict. If you believe the contact interaction, that means you have to have something to attract the test particle. If you don't believe that, so that means you generate something where philosophically we believe there must be a contact. Otherwise, we don't generate field. Okay? So what I'm trying to do is say, okay, field also follow its own space-time, like photons. So then there is no black holes. But people say, hey, we already absorbed black holes. Yeah. So, but let's hold this for now. Okay, let's say there is no black hole. But we can have a strong gravitating object. It's not a black hole, but we can see it, but it's strongly interacting object. Okay, if field goes out from a source, does it come back? That's a very basic question. Okay, we have field goes out. Okay, does it come back? If it's not, then all our particles are going to keep emitting field forever. Okay, so sooner or later we're going to be out of ammunition or the field. We don't have it anymore. Okay, so the current mainstream physics say they don't care. Okay, if we ask a classic question, say, okay, if field goes out, it comes back. Okay, so let's look at the Newton's law of gravity. Okay, we have 1 over r squared. That's a surface density. Okay, physically makes sense. You ask yourself, okay, it's not a surface density, the force. It should be number density. Surface means area of 2-dimensional. I think should be 3-dimensional, but we have a 4th dimension per unit time. Surface density means surface per unit time. Okay. Now if we have number density, then what we need to do is we need to introduce, to modify this part of G. We can absorb the modification, the field comes back. That's a frequency of field keep emitting. If field goes out, come back, go out, come back. Because otherwise the field is on the road. If per gram of material has certain amount of number of field can go out. Okay, so if we allow G, gravitation constant, to inversely proportional to the radius of the boundary or where it comes back. Okay, the field comes back. So that's my assumption. If field comes back, then we have a radius. Where it comes back, it goes out, come back. It has a boundary, okay? So the question, the field goes out, does it come back? If it comes back, then it has a boundary. Then we're able to allow us to introduce a radius of the boundary. It makes more sense because now we have r squared. Now if we have another r, that's r cubed. But this r is different from this r. This large r, it's the boundary. Because if the field R is very small, the field goes out, come back, field goes out, come back. It's more frequency so that we interacting more frequently. So imagine that we have a ball, keep shooting, okay, keep coming back. So if it come back quicker, so you will see a lot more field. Because if the radius is so big, the field goes out, then they come back, they're on the road, okay? Especially the mainstream say they don't care. The field goes out, they never come back, okay? So you lost all the field, okay? So the interesting is by introducing the gravitational constant, it's inversely proportional to the radius of the object, okay, of the boundary. So we are going to be able to bring the strong interaction, gravitation, into the same equation. And this interaction also, because it varies with radius, okay, so it may be able to bound the electrons or whatever particles, okay? So that's the second question we asked. So the third question is, what is the virtual particles, okay? Okay, so because we have infinities. And the first two questions we're asking, it's about to see gravitation. Now this one, we're now getting into the infinities of the current mainstream physics, okay? So the question is, does electron, photon, or quarks has internal structures? The current physics say no, there's no internal structures. But you see that we see an electron, okay? It's emitting a virtual particle, okay? The virtual particle, okay? We got an infinity. That's where here the infinity, because the cutoff goes to infinity. The integration term goes to infinity, okay? So that's the current mainstream physics. But if we allow the elemental particle has internal structures, then we can quantize. We can use the ultraviolet catastrophic in the 1900s, okay, where we can use it again, okay? So we can introduce the Planck term, okay, to remove the infinities, okay? So the next one, the question number 4. If the electron, photon, they have internal structures, what's binding them together? Because especially the electron, they have charges, okay? They have charges. They are repulsive because they're all negative charge. They are repulsive. So what's binding the electrons, okay? So the current mainstream physics say we no need to ask this question. But I'm proposing a self-interacting field which binds all the elemental particles, the photons, electrons, and the quarks are together because of the new field, okay? Which can be the strong interaction, okay? Because the electron also has the spin. I think if it has spin, that means it has internal structure. But the current mainstream physics is saying, okay, I don't care. This is why I think by asking those questions, if we're trying to answer that, we're looking into a new direction of physics, okay? This is a new direction. This is why when I ask these kind of questions, people say, hey, Q, what are you asking? We don't ask those questions. But as physics now have so many issues, if we don't look it back to the classical questions, we're going to be in trouble. Because if we don't look at the physics from the, basically we go back to the 1900s, we revisit what's happening. So we all know there is a strong interaction, but the strong interaction can reach out 10 to the 15, that's a nuclei or proton radius, okay? Proton radius, okay? Can reach beyond that, okay? But when the strong interaction was first proposed, Yukawa proposed that, okay, there is a mediating particle called pion, and then they found pion. And then Yukawa get the Nobel Prize because of that. Okay, but now we're saying, oh, okay, strong interaction is not mediated by pion. Okay, but pions still participate the strong interaction. If we now assume that, okay, so current mainstream physics is saying that strong interaction cannot go beyond that, okay? So, but I'm saying I don't care, okay? Now let's propose a new field, okay, which mediates the strong interaction, okay? So now you see, if we see the pion shelf life, mean lifetime span, it's this. We have, this 10 to the 8th, okay? So that's the speed of light if the pion travel like that, okay? So, okay, yeah. So it can reach to 7.8 meters. The pi 0 can reach to angstrom, 40 angstrom. So, but people said, hey, Q, it's the strong interaction, you have pion, you have gluons, it seems fine. Why you are doing something, asking this question, okay? Yeah, so okay, because what I'm trying to propose over here, can this very strong interaction reach to the macro scale? If we allow the pion to be a mediating particle, but do we have virtual pions, or what's going on here? So let's say, okay, the pion can do this. That means the very strong interaction can reach to the quantum part, okay, quantum mechanics scale, okay? That's the quantum mechanics scale. That's the macro scale, okay? So that's question number 5 I'm asking, okay? So the next one, what we have over here, yeah, is quantum mechanics complete, or it's only an intermediate description, where Einstein, the EPR, okay? So they're trying to propose that quantum mechanics is complete or not complete, okay? So the paradox, so that's where the Einstein and several other people trying to see that whether quantum mechanics is complete. Currently proof that quantum mechanics is perfectly complete. But can we have a new physics to rederive the quantum mechanics, okay? Instead of, yes, let's say quantum mechanics is complete. It's good theory, but can we derive that theory from another theory, okay? So that's what I strongly believe quantum physics is intermediate description of quantum behaviors. So that's the 6 questions we have. As I said, the most important part of physics problems, it's a dark matter issue, okay? So let's see here, what's the dark matter trouble we have? Okay, this is a typical rotation curve of galaxies, okay? This is our Milky Way, okay? I think the observation near our Milky Way, it's best observed. If we want to, basically our solar system is somewhere over here, okay? Somewhere over here, okay? So now we see that the red curve, it's what we calculate, because how to calculate the rotation curve? Based on Newton's law of gravity, we have the absorbed matter, all those bright spots, that's stars or stars, okay? Similar to our solar system. So if we count that, then we can calculate the rotation curve, the speed, where the calculated one is somewhere over here, okay? But what we observed, it's much bigger. It's somewhere over here. And also the peculiar property of the dark matter, it's almost constant, okay? So that's where the trouble we're having. There are some physicists who propose that Newton's law of gravity can be modified like that, okay? Instead of r squared, it's an r, okay? I mean, that's a centrifuge force. So then, based on if it's 1 over r force, that's the rotation curve, it's a constant, okay? So that's where, I mean, that's a theory. But now most of the mainstream people thinking the dark matter is from something dark, okay? We didn't see, okay? But there are two ways to solve this problem. One is to find the dark matter. Another way is to find a new theory, okay? I'm more inclined to find a new theory instead of finding dark matter, okay? So this R force can solve that. But the only proposed 1 over r force, it's not a final approach to solve the all physics problems, a lot of physics problems, okay? So the next one, this is the summary of the questions I'm asking. It's all very classic, okay? Any person who has graduate school or high school, college degrees or science, yeah, so they can, they understand the questions, okay? What comes out black hole to attract the material outside of that? If the field goes out, can it come back? And the photon and the quark has internal structures. What binding they charge together? All these 6 questions, it's very basic. So why I'm proposing this new direction of physics? Because the current physics is basically a lot of mathematics models. So I'm trying to understand from the physics aspect, okay, from the classic part. So, I mean, in the end, we need to have a mathematical model to revisit the general relativity, okay? So, but for now, for this next 15 video, or 14, including this one is 15. So next 14 video, we're going to show how we start the self-interacting field theory, how we derive some or solve some of these problems. So in the next 14 video, I'm going to show that a new unification scheme, because Einstein proposed that to unify all the field theory, okay? So the current physics has a standard model. You have electromagnetic interaction combined with, unified with weak interaction, and then standard model add the strong interaction, okay? So it has a mediator, okay? But they leave, what's interesting is the current standard model leave gravity out, okay? Because gravity, it's a curvature and also has some unique properties. So where do we start, okay? My new direction of physics, I'm proposing the self-interacting field theory. We're going to start from gravity, okay? We're going to rewrite Einstein's general relativity and then to derive, to see what's happening, okay? So basically, my new scheme is we put the strong gravitation, strong interaction, quantum interaction, and all the interaction which bind all the elemental particles together into one field called self-interacting field, okay? The source of the field produced by energy momentum, okay? I mean, the current Einstein's general relativity, okay, it has a energy momentum as a source of the field, okay? So I'm using the same, but I modified Newton's law of gravity and the general relativity to make into all this interaction into the same equation, okay? So, I mean, the electromagnetic, it's all related to rotation. That's my own scheme. So coming into mathematics, that's physics, okay? Coming into the mathematics, the current mainstream, they have a long linear term introduced from the long abelian group, okay? So if you have a graduate school physics background, you understand what I'm saying, that the nonlinearity, because of the sometimes known as a long commute group, it's a group of it's a group which they don't commute, then you introduce the nonlinear term. That's gauge theory, okay? Gauge, G-A-U-G-E theory, okay? I mean, the current popular one, standard model, it's SU2, okay? Group. So, but my nonlinearity, it's coming from the self-interaction, okay? So that's what's very different, okay? Just one couple of assumptions we're bringing into the self-interact, and then we bring the nonlinearity part, okay? So this is the new direction of physics I'm proposing, okay? So the next video, we're going to talk about the self-interacting field theory, okay? Which the assumptions. Let's first talk about the assumption and its implications, okay? So that's for this video. Thank you for watching.